Today I will start with how to calculate stresses and how to check these stresses according to ACI. And we have some examples we need to cover. But before starting, we need to go back to strength of material or mechanics of material. Guys, if you have a beam simply supported under the effect of uniform distributed load, the bending moment diagram for this beam will be like a parabola. The maximum moment at this point, M equal W L square divide 8. Actually, if this beam looks like this in an isometric shape, this bending moment diagram, which is positive, will cause a moment like this. We have tension at the bottom and we have compression at the top. In between, we have a line which called neutral axis. So the effect of this load on this beam will make bending moment diagram like this one. What is the value here? Maximum value W L square divide 8. What is the effect of this moment? This moment will cause tension at the bottom, compression at the top, and we have in between here a line called neutral axis. And this distribution of stress can be called stress distribution. Do you remember something like this? Stress distribution. I'm talking about plain concrete without reinforcement. I'm talking about concrete. We have no cracking. We have tension. We have compression. We have in between something called neutral axis. From strength of material, you learned that this stress equal M time Y divide I. I is the moment of inertia, parallel H cube over 12, Ix. Y is the distance between this neutral axis and the top fiber, Y1, or the distance between this neutral axis and the bottom fiber, Y2. If you are looking for sigma compression, it will be M time Y1 at the top fiber, because at the top we have compression. If you are divide I. If you are looking for sigma tension, it will be M time Y2, the distance between this neutral axis and the bottom fiber. Why bottom fiber? Because at the bottom we have tension, divide I, the same I with the same moment, but we have different Y. Probably we have different Y. So I can, from this one, I can, if you give me a beam with uniform distributed load, I can figure out the stress distribution, and I can tell you what is the tensile stress here and what is the compressive stress there at this fiber and this fiber. Any questions so far? Any questions so far, guys? Do you have any question for this point? It's strength of material. You should learn all of this stuff from this course. Or engineering mechanics. No, it's strength of material. Okay, second one. We learned also, if you have a beam and this beam has a centroid. And we have compressive force F at this centroid. We can expect stress called sigma equal this force divide area. Do you remember that? If you have axial force on a cross section, we have compressive stress. This one will be compressive. Equal this force divide this area. And the distribution of this stress will be uniform. Compression, compression, how much? Force divide area. The same value, uniform distribution. One more time. If you have moment due to the effect of a given load, this moment will cause tension in one side and compression on the other side. And in between, we have neutral axis. But if this cross section under the effect of axial compressive force at the centroid, this force divide the area of this cross section will give you compressive stress sigma, and this compressive stress is uniform distribution. Second one. So this is the first one. This is the second one. Third one. What will happen if this beam has a centroid here and your compression force F at distance or eccentricity E? The applied compression or compressive force is not at the centroid of the cross section. No, we have eccentricity E. That means this beam by superposition can be like this. We have a beam. I can assume or I can move this force to be at the centroid, F. But what about the eccentricity that was exist? So this case must be added by a moment, and this moment equal this force times the eccentricity. If you have a force and this force acting with eccentricity E from the centroid, I can make something called superposition. I will assume this force acting at this centroid, but plus this force time this eccentricity will make moment, making a compression at the bottom and the tension at the top. The first case will give you uniform stress, compression, compression. How much? How much? Force divide area. Okay? The second one will give you, we have a moment. We are under the effect of a moment. And this moment equal force times eccentricity. This moment will cause compression at the top, at the bottom, tension at the top, and we have in between, we have neutral axis here. Can you tell me what is the value of this compression at the bottom? Okay. This value of moment time y at the bottom, y2 divide r. What is the value of sigma tension equal? This value of moment time y1 at the top, divide up. We learned this. That's right. So if you understand these three situations, you are done. You're almost done. If we have external force like dead load, life load, these values of load will make bending moment looks like parabola with a value WL squared divide 8. This moment will make tension at the bottom and compression at the top, and that makes sense. If you would like to calculate the stresses at the bottom and the stresses at the top, okay, we will use this expression, sigma equal my divide I. M coming from this value, WL squared divide 8 from the given load. Y based on, are you looking for the top fiber? So we are looking for Y1. Are you looking for the bottom fiber? So we are looking for Y2. I P H cube divide 12. Second case, if you have this one called concentric force. Concentric means the applied force coincide with the centroid of the cross section. So we have uniform stress distribution compression. This uniform stress, the value equal F divide area. But sometimes, it's not sometimes, all the time for pre-stressed, we have something called eccentric force. Eccentric means the applied force has eccentricity or has a distance far away from the centroid of the cross section. In this case, we have two effects. The first effect, this force, I'm gonna move it to the centroid to be concentric. So we have a stress uniform. The value is F divide area, compression. Plus, this force to be moved to this centroid, I have to multiply this force by E to make a moment. And this moment in this case will make compression at the original location of the force. So we have compression at the bottom. And we have tension at the top. And we have neutral axis in between. And if you would like to figure out the value of these stresses, we need to use the original value for sigma equal my over I, y based on the distance to the top or the bottom fiber. Any question so far? Guys, do you have any question? Okay. I would like to tell you something. What is you need to tell us about? For any beam, we have a support here and another support for any pre-stressed beam. We have dead load and the live load on the beam. So we have W. Also, we have a centroid for this beam. Also, we have a tendon at the bottom of the beam. This tendon is pre-stressed. So the effect of this tendon will apply compressive force here, F, and another compressive force here, F. Can you tell me the final stress for this combination due to the given load, due to the pre-stressed force? So I think we have this case plus this case. Okay, go ahead and add this stress plus this stress plus this stress and tell me what is the final stress. Do you agree? Do you agree? The final shape of the pre-stressed beam, we have a beam simply supported under the effect of dead load and life load, and we have pre-stressing force, which is called eccentric. Eccentric. That means we have eccentricity, E, between the force or the tendon and the centroid of the cross-section. So we have different scenarios. I will solve each scenario alone, then add them together to figure out the final stress. Based on the final stress, I can make a check. Based on the allowable stress, ACI give you the value of the allowable stress. So we need to make a comparison if you are safe or not safe, if you are good or not good. Any question? Yes. Three. Actually, it's two cases. Case number one, we have uniform distributed load. Case number two, we have eccentric force. But case number two will be divided to two cases, eccentric and another moment, like we did here. For case number two, we have eccentric, so I will divide it to two cases, the concentric and one more time for moment. Looks good? It's very easy. It's very easy, nothing new, but we need to understand what's going on. I will start. I will cover what is the meaning of this allowable. It's a piece of cake, but I need to highlight something also. Guys, we have two times we need to check these stresses. The first time, immediately after releasing. The second time, under the effect of surface load. I'm sorry, I cannot catch. What do you mean? Okay, we have two scenarios for pre-stressing technique, for the pre-stressing technique. The first scenario, immediately. Or initially. Or just after applying pre-stress. Second one, probably after 1 year, 2 years, or I can say under the effect of surface load. The bridge is used for many months, many years, so we are talking about long time. What is the difference between this case and this case? Anybody know? What is the main difference between if you are here or if you are in this side? What is the main difference? Do you have any answer? Time. Okay, time. What is the effect of time? Yeah, I know it's time. So what is the effect? Creep. Okay. What else? No, I need one word, because if you will say creep, I will say shrinkage. Someone else will say different thing. So I need one word express all of these factors. Deformation. That's right. I don't like everybody to say different words. I need one word to include all of these words. And I told you, and I covered it last meeting. The only difference between this side and this side, yes, I know it's a time, it's a shrinkage, it's a creep, it's but the only difference between this situation and this situation is losses. Because if creep happened, we will lose some of the pre-stressing force. If shrinkage happen, we will lose some of the pre-stressing force. If deformation happen, we will lose. If time by the time, we will lose part of the pre-stressing force. Do you remember that? Pre-stressing losses. We have several factors, several effects tend to reduce the pre-stress. So if you are constructing a building or a bridge and you are immediately release the pre-stressing force, you have something called FI, initial pre-stressing force. But if you are talking about surface load after long time, no, we are talking about F only, which is surface pre-stressing force after losses. The difference between this one and this one is losses. There is one more difference. Can you tell me what is the other difference between this side and this side? Failure. Burak, we don't need failure. Failure is a jail. No, we don't need failure. What is the difference between this side and this side? We need our structure to be safe here and safe here also. Okay, I told you, you are immediately released the pre-stressing just after applying pre-stressing. I believe the bridge is not in the surface yet. So you are talking about dead load only. By time, after 1 day, 2 days, 3 days, 5 days, 1 month, the bridge became in surface, is used. So we have dead load plus live load. So please read your problem carefully. If I'm talking about immediately under construction, immediately after releasing pre-stress, so please keep in your mind, you are talking about dead load mainly on weight of the structure or on weight of the beam. And the pre-stressing force is initial pre-stressing force. But if you are talking about this bridge later, after considering all losses, we have a different value for the pre-stressing after considering these losses. And also the bridge is in use. So I will consider dead load and live load at the same time. Let me start with the first example. Wow, it looks like strange for me for this cross section. We have a cross section looks like T. It's not a regular T, but it's a T section. So, or I, we have a pre-stressed concrete I-beam. Section is shown below. Perfect. The section properties is given. The section properties are given. The neutral axis is located 13.73 inch below the top fiber. So this one is the neutral axis. At this location, we have the centroid of this cross section. Based on the geometry of this cross section, the eccentricity for the pre-stressing equal how much? 21.65 inch. The distance between the strands, the tendons, and the centroid of the cross section. Do you agree? Before starting, before completing the reading, complete the reading of the problem, I can figure this out. So the neutral axis is given. That means the centroid of the cross section. The distance between this centroid and the location of the tendons can be called eccentricity. Pre-stressing tendons with area 5.8 inch square. The area PS, I will call it P, because area steel, area S is the area of reinforcement without pre-stressing. So PS pre-stressed. The area of tendons equal 5.9. Ultimate stress 270. Initial pre-stress 0.75 FB ultimate. I have question. Initial pre-stress equal 0.75 time what? FP ultimate, which is the ultimate stress, which is 270. So the initial stress is 0.75 times 270. It will be 202.5 KSI. Anybody can tell me what is the initial force? This is the initial stress. What is the initial force? Okay. Any stress equal force divide area. You are looking for force in these tendons. So what is the area of these tendons? 5.9. What is the stress in these tendons? 202.5. Can you tell me what is the force? Yes, I can. 1194.75 kip. The initial pre-stressing force equal 1194.75. How can I get them? The problem gave me the initial pre-stress. Stress 0.75 FB ultimate. What is the value of FB ultimate? 270. So 270 times 0.75, I can figure out the initial stress. This stress times the area of the tendons, I can figure out the force, the initial force. Pre-stress losses equal 32 KSI. So if you are looking for pre-stress after losses equal 202.5, which is the initial one, minus the value of these losses, 32. So I can figure out the final value for these stresses will be 170.5. So what is the value of F after considering all of these losses? Will be 170.5 times the area of tendons, which is 5.9. So I can figure out the final pre-stress force, 1005.95 kip. Guys, you are lucky in this problem because the problem gave you everything in stress format. Initial stress, stress losses. So initial stress time area of the tendons, I can figure out the initial pre-stress force. Initial stress minus stress losses, I can figure out the final stress. This final stress times the area of tendon, I can figure out the final pre-stress force after considering the losses. Do you remember what I told you here? We have two situations, just initially after releasing the pre-stress and finally under surface. The difference between this one and this one is the losses. Any question so far? Any question so far? Okay, what's going on? Are located 12.2. These terminals located at distance 2.2 from the bottom. That's fine. The applied bending moment due to dead load and the live load is 1,400 kb/foot acting on the beam. The gravity loads produce convex curvature on the bottom surface. Anyway, calculate the flexural stress on the top and bottom fiber of the cross section due to a combination of the pre-stress force after all losses. That makes sense. Why that makes sense? Because you will consider dead load and the live load at the same time. So you are talking about this stage of loading. Okay. So right now we have a beam. This beam under the effect of M coming from dead load plus live load equal, it's given, you are lucky, it's given, 1,400 kb/foot. This moment will cause tension at the bottom, compression at the top. We have neutral axis in between. This stress equal this moment time y divide r. We need to figure out the value of sigma tension at the bottom. Okay, the value of moment 1,400, but it's a kb/foot and everything will be in inch, so I will multiply it by 12 to be kb/inch. What is the value of y at the bottom? Can you tell me from the section geometry what is the distance between the neutral axis and the bottom of this cross section? This is y. We can call it y bottom. And this distance is y top. So what is the value of y bottom? It will be 21.65 plus 12.2. This distance will be 33.85. Guys, this distance in inch, so I multiplied this moment by inch. Divide inertia. If you look here, there. We don't have moment of inertia here. The moment of inertia is not given. The moment of inertia is not given. So I will change my strategy. If you go back also to strength of material, sigma equal M divide S. S can be calculated by inertia divide Y. So from this term, if you push Y to the bottom, I divide Y, this term can be called S. Elastic section modulus. If this Y at the bottom, this S will be at the bottom. So S bottom coming from Y bottom. S top coming from Y top. So we have two scenarios. Probably, if moment of inertia is given or you can calculate it, go ahead and use my divide I. Sometimes these cross sections are given in a table, so the table can give you a value for S, which you call section modulus. So I will use this expression instead of this expression. So if you would like to get the sigma at the bottom, which is tension, it will be M divide S at the bottom. M 1400 times 12. S at the bottom is given 1038. I can get the value. Sigma at the top, which is compression, equal M divide S top. 1400 times 12 divide S top 2560. So I can figure out these values. 16.18. 6.56. So guys, this tension is 16.18 and this compression 6.56. Any questions so far? Any questions so far? First one, or first step. So this part is clear. You should be familiar with this. Sigma equal my over I, or sometimes M divide S. In this case, S can be called section modulus. Second one, we have, I will assume this cross section with force F concentric. Your sigma, which is compression, equal this force divide the area of the cross section, and the stress will be uniform, plus this cross section under the effect of a moment. This moment equal F time eccentricity. So your moment in this case will equal the force F. I will use after losses 1005.95 time eccentricity. Do you remember what was the value of the eccentricity? 21.65. So this value, remember this one in Kemp, this eccentricity in inch. So the final value will be Kemp inch. And this stress will be 1595 divide area. The cross section area is given here 283.8. This stress will be 3.54 kb per inch square. And this one is compression. Sigma at the top, sigma at the bottom, or sigma. We will have tension here, we will have compression. So sigma tension at the top, sigma compression at the bottom, equal M divide S at the top, M divide S at the bottom. We have a new moment. 778.8. This point. Okay, divide S at the top. 256. This value will be 8.5 tension. This value will be S at the bottom, 1038. No, I have a mistake here. $20.98. So by the end, we have three cases. I have compression, I have tension from the given load, tension 16.18, compression equal 6.56. Plus, we have uniform compression 3.54, 3.54 coming from this case. Plus, third case, we have tension at the top 8.5. We have compression at the bottom 20.98. What is your final stress? This one is compression. This one is compression will be added together. 6.56 plus 3.54 minus this value, because it's a tension. This one is tension. This one is compression. This one is compression. So please give me the final answer and tell me, is it the final tension or compression? So the final will be compression 1.6 compression. This one is tension. This one is compression. This one is compression. So 20.98 plus 3.54 minus 16.18. The final will be 8.34 compression. This is called final stress. Here is the top, here is the bottom. And remember, this is stress KSI, K per inch square, KSI. Any question? Any question? Do you think these stresses are safe or not safe? Actually, he didn't ask for the safety because if prime C is not given. So skip this step right now for this problem. We need only to figure out the stresses at the top and the bottom, the final stress. So just to remind you, this stress distribution D2 dead load plus live load, which was given by M equal 1,400 kb foot. This moment was given. You are lucky. The second one, if you have is a concentric force F at the centroid. So we have force divide area. That's it. The third one, because you have eccentricity, so this force times eccentricity will give you a moment. This moment will make compression and tension, and we have neutral axis in between. All of them at the same time, so we need to add them together. Please be careful to figure out which one is compression and which one is tension, because the compression stress will be added minus the tension one. In this case, we have tension, we have compression, we have compression. So the final stresses, all of them are compression. That means all of them compression. That means no need reinforcement. Guys, do you remember what was the main purpose for pre-stressing? We don't need to use reinforcement. Why? Because we don't have tension in concrete. However, you have dead load and the live load, but the final stress is still compression at the top, compression at the bottom, so we don't need any reinforcement. And that makes sense. It's a good question. It's a very good question, guys. You are talking about section properties. Okay, I can show you something here. Cannot remember. Okay, probably this one here. This is the manual for PE. If you are looking to prepare yourself for PE, it's 1,648 pages. Pre-stress concrete. Here you go. There is a code called PCI for pre-stressed. It's a different one. It's not ACI or ASCE. No, it's a different code. You will have given these beams with different dimensions, type number 1, type 2, type 3, and you will given a tables, many tables. So you can get in this table with the girder type, so you can figure out what is the depth, what is the area, what is the center of gravity, what is the moment of inertia, what is the section modulus, everything. So these are called ready cross-section. In the next semester in spring, you will learn steel design. For steel, we have tables for any cross-section of steel. So these are beams with cross-section, and these cross-section, you can figure out the section properties using tables. And these tables are provided in the codes. That makes sense? But if I'm talking about rectangular cross-section, no, you can figure it out. You can figure I, which equal, for example, this one is 14. This one is 24. So moment of inertia is 14 times 24 cube over 12. Centroid adhere. So this distance will be 12. This distance will be 12. So sigma equal m y divide r. I can figure it out. Y, this distance if you are talking about the bottom, or this distance if you are talking about the top. That makes sense? But if your cross section is complicated, and probably you can expect something like this in the exam, like this one. But promise, if you are given this type of cross section, I will give you the section properties, because as you know, the section properties is given in table. No, don't worry. If I give you different cross section, I will give you the section properties in the problem. Okay, if you look to the homework, all of them are rectangular. Don't worry. Okay. Next time, I will do more examples, and we'll start with the deflection. Deflection is a piece of cake, just one sentence, you are done.